Hello and welcome to section 2.1, the derivative in the tangent line problem. In this section we're going to kind of answer one of the questions that calculus was we're going to talk about one of the questions that calculus was trying to answer. And one of the questions that they were trying to answer was, could you find the slope of a tangent line at one particular point on any curve? And so what this basically means is, first we need to talk about what a tangent line is. And you probably remember from geometry class or maybe trig class that a tangent line is a line that touches a point and is perpendicular to the radius of a circle, touches the circle at one particular point and is perpendicular to the radius. But then how does this work when we're dealing with curves? Well, when we deal with curves, it's a little bit trickier. But you'll notice that, for an upside down parabola like this, or any shape that's like this, you could have a point, and you could have a point and then have a tangent line, and it's fine. It still only touches at one point, and if I could draw a straight line, that would work too. And then this guy right here, because we defined it as it doesn't ever cross the curve more than once, and so, does not cross the curve, and so, well, it doesn't really work for the second one, or possibly even the third one. So basically what we're going to talk about when we're talking about tangent lines is just a segment. It's a little segment that will touch the curve at one particular point. It may cross it at some time later on, but at that particular point we're going to have this little segment that we're going to find that's only touching the curve at that one point around that point. So then, how do we find the tangent line? Well, we can go through and find the slope of the tangent line at any particular point, and this is basically how they went about doing it. They basically said, okay, if I draw a curve and I pick 2 points on the curve, I have a secant line. Well, a secant line is going to cross the curve at 2 particular points. But they realized, using limits, that if they were to push these 2 points ever closer and closer together, and if we make it that they're so close that they look like they're the same point, then you are possibly getting a tangent line at one particular point. So all of this is basically talking about we're using a secant line to approximate the tangent line. And so we started out this f of c plus x minus f of c is basically our change in y that we talk about for slope. That c value, or this little delta, the c value is some point, and this delta x is a really small difference between that point, the two x values. So I might choose an x, like if x was 1, then my delta x would be maybe something like a whole bunch of decimals with a 1 after. So this thing is really close. So that's why this bottom part would just be delta x, because it would be so close that we could barely tell the difference between the two. So the whole idea is that we're going to take this secant line and push it ever closer, and we end up with the tangent line. And so we will do this from the right hand side. We get the difference quotient. This is kind of an important thing. And we're dealing with basically a change in y over our change in x. So our change in x is the delta x that you see on the bottom, and our change in y is the numerator, some value that we're trying to get real close to c, and we're pushing this x value ever closer to it. And we can talk more about this in class, but please ask if you have questions. So then we have the definition of a tangent line, and the definition of a tangent line, as you can see, has a limit in it. And so if we make that delta x really small, we're going to push these guys really close together. And so this right here is very important, and we need to know this for our test. And so if they ever ask you to do the limit process of a derivative, or using the limit process find the slope, this is what we're going to do. And we will do examples of it in class so that you can get what it is, but make sure you have this down and make sure you know what this is. And so for the slope of a tangent line at a particular point C, we would use this function up here. And so all of this is based off of the slope that we learned in geometry class. All of this is based off of just getting in the limits that we just learned in the previous unit, is how can we get these guys ever close to the point, and by doing that we will end up with the actual slope of the tangent line. So then here's a little bit more about it, and basically what we're saying is the definition of a tangent line does not cover the possibility of a vertical tangent line. So if that would happen, we would end up with this derivative would come out to be, this limit would come out to be infinity or negative infinity, and that's how we're going to know that we end up with a vertical tangent line on a graph. And so occasionally we're going to ask you to find a vertical tangent line, and basically as usual we're going to be picking an interval, and if we end up with infinity as our limit, then we would have a vertical tangent line. And so you can kind of see a picture here. This is one where it's not an asymptote. This is one where we get a vertical line in the graph as the graph continues. So all the way up to that point, there is a positive slope, or there's a positive slope, and then it still has a positive slope over here, but we would just have at one little point right here, C, we're going to have a vertical line. So then the derivative function, like I said earlier, is this, using the limit process, is this, and we need to make sure this is the definition of a derivative. And so if they ask you to take the derivative, that's part of one of our operations of calculus is differentiation, which helps us find the slope of a tangent line, is this function right here. And like I said, when you come to class, that's the reason why we're doing these videos, so that when you come to class we can practice this, and you guys can get as much practice as you possibly can on this, because this is not necessarily an easy concept to get right away. And so, you know, we're just basically going through, and we're going to treat this as a limit as we normally have. You may notice there's some new notation here. This f with a parenthesis type thing. It's a little mark here that says that's the derivative, and so that's our new notation. And so that's the derivative of this function with respect to x. And so then we have a bunch of different types of notation. All of these mean the same thing. This is change in y over change in x, dy over dx. This is y prime, which is saying the derivative. This says take the derivative, d over dx is take the derivative of f of x with respect to x. And then this is a notation that they use, but we very rarely see it. So of all of these guys, probably the only other one that I didn't write down, which you saw in the previous slide, was that. And so all of this is saying, all of these guys are saying the exact same thing. They're saying take the derivative of y with respect to x. That's what this says, that's what this says, that's what all of these guys say. And so we're taking the derivative of the function with respect to x. And we know that's respect to x because it's on the bottom of the function in this case. And so that's what we're doing. But all of it means this down here, the limit process. And like I said, we will practice this in class. So then we talk about differentiability and continuity, and there is an alternate form for the derivative. And basically what this is saying is, okay, so let me go back here real quick. This derivative process right here, this derivative or limit process works all the time. And this one will work. It's not supposed to have an H in there. This will work all the time no matter what. You could do any point, you could do a particular point, you could get an answer that has x's in it, you get an answer that has a number in it, whatever, but this one works all the time. And it doesn't have to approach it doesn't have to approach a certain value for this one to work. Over here, this one works well as long as the function is continuous and we are approaching a particular value. So this is the same thing, but this may look very familiar to you, that we are dealing with a change in y with respect to a point. And so this is a particular case. These guys work really well if you know what value you're trying to find the limit of. So like at what point you're trying to find the derivative, at what point you're trying to find. So if I gave you a function like x squared and I wanted to find the slope at, or the derivative at, say when x was 2, I might use this alternative form instead of going through the whole limit process. I mean, you still have to do a limit, but it gets rid of some of the variables and things like that, which the limit process can get cumbersome, and so this will make it a little bit easier. But the limit process that I showed you over here, this limit process will always work. It'll even work for when you approach a certain x value. What happens is you need to go through this process, you get the answer, which will be some kind of equation, and then plug in the number that they gave you, like x equals 2, or the c value. In this case, you would go through, plug it in right away, and then do the limit process, and you'll get the same answer. You'll end up with the same answer either way. And like I said, we can talk about these in class. Please come to class and ask questions. Make sure you get these down, though, so that you have them. And so this is a proof of it. It's in your book. You can go ahead and look at it. But basically what they're saying, it says, if f is differentiable at x equals c, then f is continuous at x equals c. So if you can differentiate a function at any particular point, so if you can find the limit as it approaches a value at the particular point, then the function is continuous. And that kind of goes back to what we were talking about before when we were dealing with the functions where we would change them from like f of x to g of x so that we could get rid of the whole, and we'd use g of x as a direct substitution. Well, that new function is continuous at all the points, so therefore we could differentiate and find out what's happening at that point. And so that's really what's happening, and this proof down here kind of shows you that, and we can talk more about it if you have any questions. Whether you need to know this proof or not, you probably don't need to know it. You won't need to know it for the AP test, and I won't be testing you on it, but it's something good to kind of look at. And so then here's our summary of what's happening with continuity and differentiability. If a function is differentiable at a value like c, then it is continuous at that point. So if it is differentiable, it implies that the function is continuous. But it doesn't necessarily mean the opposite. It doesn't necessarily say that if a function is continuous, it may not be differentiable. And basically, here's what's happening. All right. Remember that when we were talking about functions being differentiable or finding the limit of them, if I gave you a function that looked like the absolute value function, okay, so let's take the absolute value function as an example. And so I'll just make the axes on here. Here's just the standard f of x equals the absolute value of x. Okay, so when I do find the slope of this side over here, I get -1. When I find the slope over here, I get +1. So the slope on this half and the slope on this half are different. Well, this is basically saying that when we find the derivative, remember, we're finding the slope of the line, and we'd find the slope of a little tangent line anywhere on this side. Well, that means that we are approaching two different values from the left and the right. One -1, one +1. So even though this function is continuous, it's not differentiable everywhere, because at this point down here, 1, we can't find the slope, and 2, we're approaching two different values. So that's really what we're talking about, that a function, if it's differentiable at a point, yes, then it's continuous. But if it is continuous, it doesn't necessarily mean that you can differentiate everywhere, even at that point. So this concludes our lesson for today on the examples and stuff. We will do more in class, so you have a time to practice this. So please come to class prepared to ask questions about the videos, and also to come to class prepared to work.